Hello and welcome. Today we're going to explore a powerful mathematical tool called the binomial expansion. This theorem allows us to expand expressions of the form a plus b, all raised to the power of n, without having to multiply them out term by term. You might be wondering why this is important. Well, the binomial theorem is used by scientists to make approximations in calculations. For example, physicists use it to analyze the collision of particles in nuclear fission, and scientists at CERN use it in computer models to calculate the collision of high-energy particles. By the end of this video, you will be able to understand the notation used in binomial expansion, and you'll be able to use the expansion of a plus b to the power of n, where n is a positive integer. Our objectives are to understand the notation n, choose r, and n factorial, and to use the expansion of a plus b to the power of n. Before we dive into the binomial theorem, let's quickly review some essential skills. First, expanding brackets. You should be comfortable expanding expressions, like a plus b squared, which is a plus b times a plus b. Let's work through an example. To expand 2x minus 5 squared, we multiply each term in the first bracket by each term in the second. This gives us 2x times 2x, which is 4x squared, minus 2x times 5, which is 10x, minus 5 times 2x, which is another 10x, plus 5 times 5, which is 25. Combining the like terms, we get our final answer, 4x squared minus 20x plus 25. Next, let's review simplifying indices. You should know how to simplify expressions like 3x squared, all to the power of 5. When you have a product raised to a power, you raise each factor to that power. So this becomes 3 to the power of 5 times x squared to the power of 5. Remember the rule for powers of powers. You multiply the exponents. 3 to the power of 5 is 243, and x squared to the power of 5 is x to the power of 10. So the simplified expression is 243x to the power of 10. These two skills, expanding brackets and simplifying indices, are the building blocks for understanding binomial expansion. Let's begin our journey into binomial expansion by looking at a fascinating pattern. We'll start by expanding some simple binomials. First, 1 plus x to the power of 1 is simply 1 plus x. Next, 1 plus x squared is 1 plus 2x plus x squared. And 1 plus x cubed is 1 plus 3x plus 3x squared plus x cubed. Now, let's focus on the coefficients of these expansions. The coefficients are the numbers in front of the x terms. For the first expansion, the coefficients are 1 and 1. For the second, they are 1, 2, and 1. For the third, they are 1, 3, 3, and 1. If we arrange these coefficients in a triangle, we get a very special pattern. This triangle is known as Pascal's triangle. Notice the rule for creating this triangle. Each number is the sum of the two numbers directly above it. For example, 1 plus 2 equals 3, and 3 plus 3 equals 6. This simple rule allows us to extend the triangle indefinitely. For instance, the next row would be 1, 6, 15, 20, 15, 6, 1. This triangle provides a quick way to find the coefficients for any expansion of the form 1 plus x to the power of n. Now, let's see how we can use Pascal's triangle to expand a more general binomial, a plus b, to the power of n. The coefficients for the expansion of a plus b to the power of n are the same as for 1 plus x to the power of n. The only difference is how the powers of a and b change. Let's take the example of a plus b to the power of 4. The coefficients are 1, 4, 6, 4, 1, which is the fourth row of Pascal's triangle. For the first term, the power of a is n, and the power of b is 0. For each subsequent term, the power of a decreases by 1, and the power of b increases by 1, until the power of a is 0, and the power of b is n. So the expansion is 1 times a to the fourth, plus 4 times a cubed b to the first, plus 6 times a squared b squared, plus 4 times a to the first b cubed, plus 1 times b to the fourth. Let's work through a full example. We'll expand 3 plus 2x to the power of 5. Here, a is 3, b is 2x, and n is 5. The coefficients are from the fifth row of Pascal's triangle. 1, 5, 10, 10, 5, 1. Now we write out the expansion. It's 1 times 3 to the fifth, plus 5 times 3 to the fourth, times 2x to the first, and so on. The final step is to simplify each term. Be careful with the powers. 3 to the fifth is 243. 3 to the fourth is 81, and 2x squared is 4x squared. 2x cubed is 8x cubed, and 2x to the fourth is 16x to the fourth. Multiplying everything out, we get our final expansion, 243 plus 810x plus 1080x squared plus 720x cubed plus 240x to the fourth plus 32x to the fifth. Let's look at another example, this time with a negative term. We'll expand 5x minus 2 to the power of 4. Here, a is 5x, b is negative 2, and n is 4. The coefficients are 1, 4, 6, 4, 1. A crucial point here is to treat the negative sign as part of the Tuskegee Dehua b term. So b is negative 2, not just 2. The expansion is 1 times 5x to the fourth, plus 4 times 5x cubed times negative 2 to the first, plus 6 times 5x squared times negative 2 squared, and so on. Notice what happens to the signs. A negative number raised to an odd power is negative, and a negative number raised to an even power is positive. This means the signs will alternate. The first term is positive, the second is negative, the third is positive, the fourth is negative, and the fifth is positive. This alternating sign pattern is a key feature of expansions with a negative term. Now let's simplify. 5x to the fourth is 625x to the fourth. 5x cubed is 125x cubed. 5x squared is 25x squared. And the powers of negative 2 are negative 2, 4, negative 8, and 16. Multiplying everything out, we get our final answer. 625x to the fourth minus 1000x cubed plus 600x squared minus 160x plus 16. While Pascal's triangle is great for small powers, it becomes cumbersome for larger ones. To handle this, we need a more formal notation. This brings us to factorials and combinations. First, let's define factorial notation. N factorial, written as n with an exclamation mark, is the product of all positive integers from n down to 1. For example, 6 factorial is 6 times 5 times 4 times 3 times 2 times 1, which equals 720. A special case to remember is that 0 factorial is defined as 1. This might seem counterintuitive, but it's necessary for the formulas to work correctly. Next we have combinations. The notation n, choose r, written as n over r in parentheses, represents the number of ways to choose r items from a set of n items. The formula for n choose r is n factorial divided by the product of r factorial and n minus r factorial. Let's calculate 8, choose 5. Using the formula, we have 8 factorial divided by 5 factorial times 3 factorial. A clever way to simplify this is to write out the larger factorial in the numerator until it matches the larger factorial in the denominator and then cancel them out. So 8 factorial becomes 8 times 7 times 6 times 5 factorial. We can then cancel the 5 factorials. This leaves us with 8 times 7 times 6 in the numerator and 3 times 2 times 1 in the denominator. This simplifies to 56. You can also find these values using the NCR button on your calculator. These combinations are the coefficients we saw in Pascal's triangle. We are now ready to state the binomial theorem. It provides a general formula for expanding any binomial. The binomial expansion of 1 plus x to the power of n is 1 plus n choose 1 times x, plus n choose 2 times x squared, and so on, up to n choose n times x to the n. Remember that n choose 0 is 1, and n choose 1 is n, so the first two terms are always 1 plus n x. This is a very useful shortcut to remember. The expansion always starts with 1 plus nx. For a general binomial, a plus b to the power of n, the theorem is written as follows. The expansion is the sum of terms, where each term is n choose r, times a to the power of n minus r, times b to the power of r. The index r starts at 0 and goes up to n. Let's break down a single term in this expansion. The term n choose r is the coefficient. The term a to the n minus r is the first part of the binomial raised to a decreasing power, and the term b to the r is the second part of the binomial raised to an increasing power. A key point to notice is that the sum of the powers in each term, n minus r plus r, always equals n. This is a great way to check your work. Let's apply the binomial theorem to find a specific term in an expansion. We'll find the fifth term in the expansion of 1 plus x to the power of 7. Our goal is to find the fifth term of 1 plus x to the power of 7. The general term is given by n choose r times a to the n minus r times b to the r. For the fifth term, we need to be careful with the index r. The first term corresponds to r equals 0, the second to r equals 1, and so on. Therefore, the fifth term corresponds to r equals 4. In our case, n is 7, a is 1, b is x, and r is 4. Plugging these values into the formula, we get 7 choose 4 times 1 to the power of 3 times x to the power of 4. Now we calculate the combination and simplify. 7 choose 4 is 35. 1 cubed is 1, so the fifth term is 35x to the power of 4. Let's try another example. Find the first three terms in descending powers of x for the expansion of 4x minus 3 to the power of 5. We need the first three terms of 4x minus 3 to the power of 5. Descending powers of x means we start with the highest power of x, which is x to the fifth. This corresponds to r equals 0. The first term is 5 choose 0 times 4x to the fifth times negative 3 to the 0. This simplifies to 1024x to the fifth. The second term is 5 choose 1 times 4x to the fourth times negative 3 to the first. This simplifies to negative 3, 840x to the fourth. The third term is 5 choose 2 times 4x cubed times negative 3 squared. This simplifies to 576 x cubed. So the first three terms are 1024x to the fifth minus 384x to the fourth plus 576x cubed. Often, we don't need the entire expansion, just the coefficient of a specific power of x. Let's find the coefficient of x squared in the expansion of 2 plus 3x to the power of 7. We want to find the coefficient of x squared in the expansion of 2 plus 3x to the power of 7. We need to find the term that will result in x squared. The general term is n choose r times a to the n minus r times b to the r. In our case, a is 2 and b is 3x. The power of b, which is r, will determine the power of x. So we need r to be 2. Plugging in n equals 7 and r equals 2, we get 7 choose 2 times 2 to the power of 5 times 3x squared. Now, let's calculate this term. 7 choose 2 is 21. 2 to the power of 5 is 32. And 3x squared is 9x squared. So we have 21 times 32 times 9x squared. Multiplying these numbers together, we get 6048x squared. The question asks for the coefficient, which is the number in front of the x squared term. Therefore, the coefficient of x squared is 6048. It's important to give just the number, not the x squared term itself. Sometimes, we need to find a term that doesn't contain x at all. This is called the term independent of x. Let's find the term independent of x in the expansion of x squared plus 1 over x squared, all to the power of 6. The general term is 6 choose r times x squared to the power of 6 minus r times 1 over x squared to the power of r. We can rewrite 1 over x squared as x to the power of negative 2. So the term is 6 choose r times x to the power of 12 minus 2r times x to the power of negative 2r. To find the term independent of x, the total power of x must be 0. We add the exponents of x. The total power of x is 12 minus 2r minus 2r, which is 12 minus 4r. Setting this equal to 0, we find that r must be 3. Now we can find the term by plugging in r equals 3. The term is 6 choose 3 times x to the power of 12 minus 12. 6 choose 3 is 20, so the term is 20 times x to the power of 0, which is just 20. So the term independent of x in this expansion is 20. The binomial theorem is also incredibly useful for approximating values. Let's use it to find the value of 1.03 to the power of 4. We want to calculate 1.03 to the power of 4. The key is to rewrite the number in the form 1 plus x. We can write 1.03 as 1 plus 0.03, so we are expanding 1 plus 0.03 to the power of 4. Since the power is small, we can use Pascal's triangle for the coefficients. 1, 4, 6, 4, 1. The expansion is 1 plus 4 times 0.03 plus 6 times 0.03 squared plus 4 times 0.03 cubed plus 0.03 to the power of 4. Now we calculate each term. 4 times 0.03 is 0.12. 0.03 squared is 0.0009, and 6 times that is 0.0054. The other terms are very small. Adding these values together, we get 1.125508881. This is the exact value. For larger powers, we would typically only calculate the first few terms to get an approximation. For example, if we only use the first 3 terms, we would get 1.1254, which is a very good approximation. Let's move on to more complex expansions, where we have a product of 2 expressions. We'll find the first 3 terms in descending powers of x for the expansion of 2x minus 4 over x, all to the power of 6. We use the binomial theorem with a equals 2x, b equals negative 4 over x, and n equals 6. The coefficients are 1, 6, 15. The first term is 1 times 2x to the 6th, which is 64x to the 6th. The second term is 6 choose 1 times 2x to the 5th times negative 4 over x. This simplifies to negative 768x to the 4th. The third term is 6 choose 2 times 2x to the 4th times negative 4 over x squared. This simplifies to 3,840x squared. So the first 3 terms are 64x to the 6th minus 768x to the 4th, plus 3840x squared. Now, let's use this result to find the coefficient of x cubed in the expansion of 1 plus 2x times our previous expansion. We need to find the coefficient of x cubed in the product of 1 plus 2x and the expansion we just found. We only need to find the terms that will multiply to give x cubed. We can multiply the 1 by any x cubed term in the expansion and the 2x by any x squared term. Looking at our expansion, there is no x cubed term. So multiplying 1 by the expansion gives no x cubed term. However, we can multiply 2x by the x squared term, 3840x squared. So the only way to get an x cubed term is by multiplying 2x by 3,840x squared, which gives 7680x cubed. The coefficient is 7,680. Let's tackle another complex expansion. We'll find the first 5 terms in descending powers of x for the expansion of x minus 2 times x plus 3 over x to the power of 9. We need to expand the product of x minus 2 and x plus 3 over x to the power of 9. The strategy is to first expand the binomial part, x plus 3 over x to the power of 9, and then multiply the result by x minus 2. Let's expand x plus 3 over x to the power of 9. The general term is 9. Choose r times x to the 9 minus r times 3 over x to the r. We need the first 5 terms in descending powers of x. This means we need the terms with the highest powers of x. The highest power of x in the final expansion will be x times x to the 9th, which is x to the 10th. The next highest will be x to the 9th, and so on. So we need to find the terms in the binomial expansion that will give us x to the 9th, x to the 8th, x to the 7th, x to the 6th, and x to the 5th. For x to the 9th, we need 9 minus 2, r equals 9, so r is 0. The term is x to the 9th. For x to the 7th, r is 1. The term is 27x to the 7th. For x to the 5th, r is 2. The term is 324, x to the 5th. So, the expansion of x plus 3 over x to the 9th starts with x to the 9th plus 27x to the 7th plus 324x to the 5th, and so on. Now we multiply this by x minus 2. We distribute the x and the negative 2. This gives us x to the 10th plus 27x to the 8th plus 324x to the 6th minus 2x to the 9th minus 54x to the 7th minus 648x to the 5th. Finally, we collect like terms and write them in descending order of power. The first 5 terms are x to the 10th minus 2x to the 9th plus 27x to the 8th minus 54x to the 7th plus 324x to the 6th. Let's look at a problem where we need to find an unknown constant. We are given that the coefficient of x cubed in the expansion of 1 plus ax plus 2x squared times 2 minus x to the power of 7 is 560. We need to find the value of a. We are given the coefficient of x cubed in this product is 560, and we need to find a. First, we need to find the expansion of 2 minus x to the power of 7, up to the x cubed term. The expansion is 2 to the 7th, plus 7 choose 1 times 2 to the 6th times negative x, plus 7 choose 2 times 2 to the 5th times negative x squared, plus 7 choose 3 times 2 to the 4th times negative x cubed. Simplifying this, we get 128 minus 448x plus 672x squared minus 560x cubed, and so on. Now we need to find all the ways to get an x cubed term when we multiply this expansion by 1 plus ax plus 2x squared. We can multiply 1 by the x cubed term, ax by the x squared term, and 2x squared by the x term. Plugging in the terms we found, we get 1 times negative 560x cubed plus ax times 672x squared plus 2x squared times negative 448x. This simplifies to negative 560x cubed plus 672ax cubed minus 896x cubed. The coefficient of x cubed is the sum of the coefficients of these terms. The coefficient is negative 560 plus 672a minus 896. We are given that this equals 560. Combining the constants, we get 672a minus 1456 equals 560. Adding 1456 to both sides gives 672a equals 2016. Dividing by 672, we find that a equals 3. Let's conclude with a final, more challenging example. We'll find the coefficient of x to the 4th y squared in the binomial expansion of 2x minus y to the power of 6. We need to find the coefficient of x to the 4th y squared in the expansion of 2x minus y to the power of 6. We use the general term formula. N choose r times a to the n minus r times b to the r. Here, n is 6, a is 2x, and b is negative y. We need the power of x to be 4 and the power of y to be 2. The power of y is determined by r, so we must have r equals 2. Let's check if this gives the correct power of x. The power of x is 6 minus r, which is 6, minus 2, which is 4. This is exactly what we need. Now we can write out the term by plugging in r equals 2. The term is 6 choose 2 times 2x to the power of 4 times negative y squared. Let's simplify this expression. 6 choose 2 is 15. 2x to the power of 4 is 16x to the 4th. And negative y squared is positive y squared. So we have 15 times 16 x to the 4th times y squared. Multiplying the numbers, we get 240x to the 4th y squared. The question asks for the coefficient, which is the numerical part of the term. Therefore, the coefficient of x to the 4th y squared is 240. Let's quickly recap what we've learned today. We started by observing the patterns in binomial expansions, which led us to Pascal's triangle. We then introduced factorial notation and combinations, which allowed us to state the binomial theorem. We saw how to use this theorem to expand binomials, find specific terms, find coefficients, and even approximate values. We also worked through more complex problems involving products of expansions. The key takeaway is that the binomial theorem provides a systematic and efficient way to expand binomials to any positive integer power. It's a fundamental concept in algebra, with wide-ranging applications in science and mathematics. Thank you for watching.